Now let's talk about chemical equations and what they mean and what the parts of them are. Here's an example of an equation for a chemical reaction. What can we see very easily from this equation? First off, we know that everything on the left-hand side of this arrow is called a reactant. Everything on the right-hand side will be a product. Anything on top of the arrow is going to be something that helps the reaction but isn't changed in the reaction. So it's not part of the reaction per se. It might be needed for the reaction to occur, but it itself does not change during the reaction. Some things that are commonly on top of the arrow are heat, light, or a specific catalyst. What else can we see? Well, you notice there's some numbers here. Let's talk about what the two different types of numbers are. The numbers here that are subscripts have a really fancy term. They're called subscripts. So you already know the terms for those. Those are used to ensure that the formula is correct. So when we write hydrogen phosphate, as you see here, you know that there should be 3 hydrogens for every phosphate because the phosphate has a 3 negative charge, so there must be 3 positive hydrogens. Similarly, when we look at hydrogen, the gas, the element here, it has to have a 2 subscript. So we can see that those subscripts help us to make sure we know we have the right compound. Those cannot be changed when we're writing the equation. We can't change those formulas because we know if I'm talking about hydrogen phosphate, the formula will always be H3PO4. It can't be a different formula. It will change into something new in the second part of the reaction, but again, those have very specific formulas. So in this case, we have zinc with a subscript 3 and PO4 with a subscript 2. And why do we have those? That's because the zinc has a 2 plus charge and the phosphate has a 3 minus charge, and to make sure that those charges balance, we get this formula. So you can't change the formula. Those will never change while you're writing these equations. So then what are those other numbers? The numbers in front of those. The number that is placed in front of an element or compound in an equation is called a coefficient. You'll need to know that term. So here we see a 3 in front of the zinc, and the purpose of that 3 is to make sure that the number of zinc atoms we have on the left-hand side of the equation, on the reactant side, is equal to the number of zincs that we have on the product side. So that number is actually a multiplier. When we look at this, we have 3 zinc atoms on the reactant side, and we see when we use that subscript that we have 3 zinc atoms on the product side. Now let's look at the next compound, and we see that we have 2 hydrogen phosphates, and that 2 is multiplied by the hydrogen, the phosphate, and specifically each part of the phosphate, so the phosphorus and the oxygens. So if we were to ask how many hydrogens are here, we would say there are 6 hydrogens, there are 2 phosphoruses, and there are 8 oxygens. And when we look on the other side, there's a 1 in front of that zinc, so there's 3 zincs, 2 phosphorus, and 8 oxygens in the zinc phosphate. So again, here we don't see the number 1, but we know that there's a number 1 there because there's some zinc phosphate. So since we didn't put the number in, it must be at least one of those. In this class, you won't be asked to figure out what those coefficients are. You'll only be asked to use them so that you know how many of each type of atom is present and to see if they're balanced out. And of course, you'll have to know the word coefficient and subscript. There are lots of symbols used as we're writing chemical equations, so let's go through what each of them mean. First off, we have a plus sign. That one's fairly simple. It means and, so that means we're adding 2 things together, and we have A and B, so you'll see an and. You'll see an arrow. It's a single-headed arrow, and that tells us that this reaction goes in one direction only. Often said goes to completion, so that means it goes all in one direction until it runs out of reactant. Then we have this other type which has a double-headed arrow, so it's going in both directions. And that term is called equilibrium, and it means that the reaction goes forward and backwards depending on what's there. So if I only have reactant to start with, the reaction will go in the forward direction. If I only have product to start with, it's actually going to go in the reverse direction. And if I have both, which is most common, we'll see that it goes in both directions at the same time. Then you'll see we have this black triangle. That means to add heat. We can also see one that is a non-filled in triangle, which is commonly used. That also means to add heat. And both of those would be placed above the arrow to show that they're part of the reaction. They help the reaction occur, but they're not really used up during the reaction. We can have this H nu, which just means light. These are commonly used on top of the arrow, again, to say that they're being added to the reaction to help it occur. Oftentimes we will also see an element or a compound written on top of the arrow, and that is called a catalyst. Those are things that are helping the reaction go, but they are not used up during the reaction. Then we have these next group, which are very common. You see the parentheses, and inside of it is the letter S, L, G, and AQ. Those are usually placed after a symbol or formula for an element or compound, and the S just stands for solid, the L stands for liquid, the G stands for gas. Those ones are pretty easy. The last one is AQ, and what that stands for is aqueous, and all that means is that it is a solution. It is something that is dissolved in water. So it's very specific about how that chemical is being used. So normally table salt is a solid, but we often want to use that when it's dissolved. So to say that it was a solid, we'd put NaCl, and then we'd put an S here. But when we add water to it, it becomes NaCl, and then AQ to say that it's dissolved. And mostly that's just because it's easier to use in the aqueous form rather than in the solid form, because it can react better when it's dissolved in water. Now we're going to put that all together and see how we can read an equation with all of these symbols. So here we're going to look at that equation we looked at earlier. It was a balanced chemical equation, which means those coefficients made sure that the number of atoms on each side were matched up. There's a few things missing from this equation, though. I'm going to add those in. First, I'd like to add in the physical states of what's reacting and what's produced. So we'll put in an S here for zinc. We're going to put an AQ for hydrogen phosphate. I'm going to put an S for the zinc phosphate and a G for the hydrogen gas. And then we're going to put one more thing. We're going to add this triangle to say that it was heated. Remember, this is how we are going to normally see them. Now what I'd like to do is how to read this. This is going to write out exactly what you would theoretically have written in a sentence, but we've shortened it down into this shorthand way of writing the reaction. There are two ways commonly used to read this. We can look at this as an atom accounting or as a mole accounting, which means that we don't have just single atoms reacting or compounds or molecules. Instead, we have whole moles of them, so lots and lots of those particles, 6.02 times 10 to the 23rd particles of them. And I'm going to show you both methods so you can kind of see how you would read these. In either case, I don't generally ask you to write out these in handwritten form, but you may see some questions about this in lab, so I just want to make sure you have an idea of how to write this equation so that when you go to lab, you'll know what to do. There will be no questions in lecture on the exam about how to read a chemical equation, but of course you need to understand it for the rest of this unit. So first we'll do this for the individual particles. As I read this, I see that I have 3 atoms of solid zinc and 2 molecules, and here we have to use molecule because this is a molecular compound, of hydrogen phosphate dissolved in water. We have that triangle above the arrow which says is heated, and then we have the arrow itself which says reacts to form, produces, yields, creates, something like that. One of those terms is used. So it makes one, and now we're going to use the word formula unit because this is a ionic compound. We're going to have to say formula unit. So 1 formula unit of solid zinc phosphate. So we need to know the names of these compounds. And, again, the plus sign means and, 3 molecules of gaseous hydrogen. I think you can understand why we like to use shorthand. Very hard to read a sentence like this, But that's what this little shorthand of the equation that we see above is saying. Now I'm going to read this again when we look at it as a mole rather than in the form of atoms and molecules. We see that we have 3 moles of solid zinc and 2 moles of aqueous hydrogen phosphate are heated to create, produce, form, yield, one of those terms, 1 mole of solid zinc phosphate and 3 moles of gaseous hydrogen. As you can see, when we talk about the mole, we don't have to tell you what the type of chemical we have. We don't have to say it's a molecule, an atom, an ion, or a formula unit. When we talk about the mole, we can just talk about it in general and assume that you know it's an atom, a molecule, an ion, or a formula unit. So you'll see that I use the word mole most of the time because usually I'm not looking at a single atom and a single molecule. I'm looking at a whole bunch of them so that I can actually see the reaction, because there's no way to see the single atom ones. They do occur as single atoms and single molecules, but it's very hard to see. So we generally, as chemists, actually use moles full of the stuff, and so you'll usually see us writing this in the mole form rather than in the atomic form. So what does the equation actually tell us? Well, it doesn't tell us a whole lot. It does tell us which substances are the reactants, which substances are the products. It tells us the physical states of those reactants and products. It tells us if something was added to help the reaction go. And it tells us how many of the atoms, ions, molecules, or moles were either reacted or produced. It's important to emphasize what the equation does not tell us. So first off, it does not tell you whether or not the reaction actually occurred. So we may have a reaction, I can write anything I want to. That doesn't mean that it can actually happen. In fact, we can have reactions that, as I mentioned, go in only one direction. Well, if I wrote it backwards, that means that reaction would not occur. And later we'll talk about how you can predict whether a reaction does or does not occur. But for the moment, you just need to know that an equation shows how something could theoretically react. It doesn't mean that it actually reacts in that way. And the second thing that it does not tell us is how fast the reaction will occur. There are some reactions that will occur as written, but they may take 1,000,000 years as they're written. So sometimes we have to add that catalyst to make it go faster, and sometimes it'll just never really happen in our lifetime. There are other reactions that will happen as soon as you add them together. They explode and they react really, really fast. So that would be something that would be what we call spontaneous. It happens super fast. It doesn't need anything to help it to go. So the equation doesn't tell us which of those we're going to have. It just says, hey, this is something that could happen. So it doesn't tell us it occurs, and it doesn't tell us how fast it occurs if it does occur. So that's the basics of chemical equations. In the next video, we'll talk a little bit about what we can do with those coefficients to see if a reaction is written correctly, at least in the way that the number of atoms are present is correct or not correct.